Thanks for joining today's webinar on reliability block diagram. I don't really think I defined it anywhere in the slide deck. It's such a common three-letter acronym for me anyway that I'm afraid I'm guilty of using a little bit too much jargon in my day-to-day work, and it comes through sometimes in my presentations. So anyway, we're going to be talking about some of the basics, really fundamental stuff, and a little bit about how to use a reliability block diagram effectively. And it's not as simple as just create a drawing or create a model. It's how you use the model that really makes a difference. And I want to touch on that a little bit. Now, we're often working to understand the reliability of our system, and we start with, well, what's the goal? Well, how long is this supposed to last, and how many failures should we expect? It might be even established in the concept phase for product development. And so the idea is we have to have a goal. We have to have some place we're shooting for. And one of the primary reasons we use a block diagram is to break down that goal, is to apportion is another term for it. We take that system goal and we break it out into the subsystems. And sometimes we go further, but it's a tops-down propagation of, well, how good do the various elements need to be? And then on the flip side, this is kind of a summary of the entire presentation, is then we gather estimates and test results and vendor results and field data and populate that model to see if we are in fact achieving our overall system goal and our reliability goal. And welcome, looks like we have a couple Canadians that joined, Florentine and Cavanavere. I'm sorry if I mispronounced that. But that's the idea. It's just a bookkeeping method to keep track of, instead of looking only at the top level goal, we break it down into smaller pieces, which are often much easier to get estimates for and to measure. Now, do you go, in your experience, and I'm sure many of you have used block diagrams in one form or another, do you break it down to components? Do you go all the way to individual pieces, or do you stop somewhere else? So jump on the chat window and let me know, one I guess, if you use block diagrams, and then how detailed do you get in creating that model? And I'll get a cup of coffee here, keep my voice going. Good morning, William. You're in the same time zone. That's cool. Or I should say, Bill, welcome. All right, so do you use block diagrams, and then how far out do you model it? Breaking it down from the system level to subsystems to components. That's kind of my basic question here. And if you don't use block diagrams, welcome. This is going to be a real basic introduction to some of the fundamentals of it. But let me know what you think. It's like a good number of people have been here before, so you know I tend to use the chat window quite a bit. To vendor subassemblies, Greg. Yeah, and that's a good idea, is to there. Let's see. We got flowcharts and subsystem defining. Yeah, they are different from flowcharts, or even a functional block diagram, which we'll often see in the requirements documents. They're similar, could be created by function. They don't have to be. But I don't know that many people break it down to all. But I don't components. You might break it down, as Greg does, to major subassemblies, or say a major component, say a CPU, for example, or power supply, for example. Now, there's lots of ways we use block diagrams. I'm going to cover that real quick. But it's basically, we don't do it just because it's on the checklist. I mean, you could, and then you check it off and you have a model. But we use the model to make decisions. We use it to help us understand a system. And even like a smartphone, is a complex system when you start digging into it and understanding all of the elements that make up its complex set of functionality. Vehicles, all kinds of different processes and manufacturing equipment and so on. Just about anything you can think of that has more than one part uh, is something that is not simple to wrap your head around the reliability of all the various pieces of that. And so I'm looking at my desk going, a pencil, a mechanical pencil's got gears and retractions and friction surfaces to hold the lead in place. It's got an eraser system. It's got ways to protect it, to reload it. There's a number of different functions, and they all have to work in order for the system to work, the pencil to work. And some of it's defined by design, some of it by the manufacturing variability. Yet, even a simple thing like my coffee pot downstairs, there's about 8 or 9 different major things that have to work in order for us to brew a cup of coffee in the morning. And when we're designing or when we're purchasing something or when we're working with a vendor, we're trying to understand what is it that impacts the reliability aspects of whatever that part is. So the heating element of my coffee pot, well, how many cycles can it go through? How stable is it at holding the temperature? And a myriad of other decisions are made about selecting and sizing that particular element. Now, one piece of that is the reliability concern of it. Well, how does it fail and when does it fail? And that's where the block diagram comes into play, is we can use the information that we gather or create estimates about to understand is it reliable enough? And we'll get into the apportionment and comparison a little bit later. But at some point, we're going to have to decide, is this part good enough for us? In other times, if we have lots of components and lots of different subsystems, lots of vendors, we probably don't have the bandwidth or the resources to improve or even want to improve the reliability of all of them. But we do need to figure out which part of the system to work on. And a block diagram is a way to help us find that weakest link to it. Now, what else can a reliability model help us decide? Is the component from a vendor good enough is one example. What else? I'm going to be asking lots of questions today, so make sure you keep your keyboard handy. But what else can a model help us to make decisions about? Few people are typing. What else can a block diagram or any reliability model help us do? I think I'm going to have to see if my coffee pot's still working. A factor in marketing, interesting. Yeah, I've run into this service intervals, maintenance stuff, bottlenecks in a process. Now, Kevin, I'd tie that one, Kevin 4, I'd tie that into a flow chart looking for the bottlenecks on throughput kind of thing. That's where I think of that. Weakest point, if you're thinking of what Alejandro's saying is the weakest part, or the weakest link, if we use the TV show. Yeah, and also I like that one, Robert, is it can help us to focus on, well, if we have an area that we know we need to improve the reliability on, well, then an FMEA might be a pretty good tool to sort out and organize what within that subassembly, that complex subassembly, should we work on. Fault isolation, you can use it, yeah, Sean, after the fact is if you get symptoms, it can help you identify where it is. I like the fault tree analysis approach a little better for that, but it certainly can help in understanding the system as to where that fault may have occurred. And there's many more, but I like the idea that it helps us to allocate resources to where it makes the biggest difference. Because if I improve the keyboard of my computer system and take it from its 5 nines reliability over 2 years to 6 nines reliability over 2 years, I may never really realize that benefit. Whereas the screen and the power supply and the CPU and the graphics card all have much less reliability than that. And so it's where do you want to put it in? Where do you want to do the investment to best improve the reliability of your overall system, or even just to meet your goal? Now, Yang, I'm tempted to jump on the MTTF calculations or estimates, but I would say I'll just leave it as don't do that. Instead of mean time to failure is use reliability. Just the reliability function. What's the probability of success over time? Mean time to failure has got so many issues with it. Go see the nomtbf.com site. Oops, with it all spelled out to see why I say that. And others can chime in there. But yeah, we use models to make decisions. Now all the models have different strengths and weaknesses and so on about how well they do. All of the models we use are wrong, right? They're not able to accurately reflect the reliability of the overall system. It is simply a model. It's something that we use in order to explore and understand the system. It's getting us a first estimate, really, at what's going on with the system. Yeah. Now, I would say it's based on random failures, Mark, but if you look at your data, we almost never, and I'll underline in bold and air quotes, never have random failures as the dominant failure mechanism for a system. There's almost always something that's decreasing. There's almost always one or more things that are increasing in failure rates. Short periods of time, it may appear constant, but it's very rare. Now, let's go back to the model. I'm being dragged into MTBF here a little bit. If I have a reliability block diagram, or I don't, if I don't have a block diagram, how do you find the weak spot in your system? How do you understand and find the area that needs the most improvement? What are some of the common techniques to do that? And I'll throw out the one that's I hope you're not doing is waiting for your customers to tell you, although that is one that's effective. It might be a little late. Yeah, so we do some proactive work like a FMEA type thing. We may do halt testing on a prototype to expose some things. Sean, you're exactly right. If we gather estimates on components and subassemblies, and the block diagram can help organize that, is look for the ones with the lowest expected reliability. And another area is the ones that we have the most uncertainty about. Our not necessarily the confidence interval, but our uncertainty around an estimate may be very large. And so if we put into the model that it could be as low as, say, 60% reliable over a year, well, then that may require us to go do some experiments or do some testing to improve that estimate. And it may or may not be the true reliability weakness, but we don't know. So I suggest that's also a weakness that we have. But yeah, field data, going off and testing it, evaluating it, engineering is judgment. All of those things help us to find where weaknesses are in a system. But once we do that, then it's a trade-off, right? We'll almost never have enough resources to improve everything. And so we want to, if we only have $100, where are we going to spend it to have the biggest impact and improvement on a system? And so we're balancing all of those other priorities that are within our organizations, within the design team and within our plants. There's cost and time to market, feature sets, and design for environment and sustainability, and the list of DFX just keeps getting longer. They're all priorities at one point or another. And reliability may or may not be the driving force, yet it should be done in balance with what else we need to make our investments in. And so the idea with a block diagram is that it allows us to quickly understand and trade off. If we reduce the cost a little bit and we give up a little bit of reliability, will we still meet our overall goal? So we can do what if analysis and we can balance cost of these other factors off to see if we're making the right decisions and we're not giving up so much reliability that it becomes a burden or it becomes financially unviable for us. So there's lots of things you can do there. But our models allow us to make decisions, do trade-off analysis, which leads to decisions, and identify areas for improvement. Again, making decisions. So it really summarizes to that. And in some organizations, it's done, we make these decisions in a program team, or we have a project manager, or a variety of different ways of doing it. Series of reviews and design reviews get included. What I submit is that without making the reliability part visible and known in a block diagram is a great tool for doing that, it's hard for the rest of the organization to understand the impact of their decisions on reliability. And so one of the key functions of a block diagram is to communicate it out to the rest of the organization of where we stand today and how decisions are impacting that. And you're exactly right, Mark. It's really great for availability discussions also, allowing us to then also trade off time to repair or diagnostics capability and all the features that make up repairable systems. And it allows us to bundle that all together. All right. Now, what's wrong with the block diagram? What's some of the underlying elements that erode its capability to be dead on accurate? So if we make a block diagram and we do due diligence and we make it all really nice and we use the best estimates we can, what are the things we need to keep in mind of why that number we get is not the actual number we're going to see in the field? It's always a good idea to keep in mind that we're making assumptions, whether we state them out loud or not. But a model is really going to be incorporating a lot of assumptions. And the simplest one is, uncertainty in our assumptions is one. Uncertainty in our estimates. If we get a vendor result data, well, exactly what conditions and how well do they know that number? How does that translate to our design and use conditions? So it's one of that garbage in, garbage out. If we use really bad estimates for the individual blocks in the block diagram, or individual estimates, then the results are very unlikely to be anywhere close to actual, right? Yeah. Well, I don't know that, William, that we need to keep in mind that there is uncertainty, not necessarily a statistical confidence kind of idea, but more of that if some of our estimates are based on just engineering judgment, there could be a pretty good range of where that estimate could be. And that's the kind of uncertainty I'm thinking of. And it may be what you're thinking of, William, but if we've got good test data, we're populating most of it with field data, but even field data, right? We don't know unless you're in a very well instrumented system, we often don't know when it was put in service, how many hours it operated, what was the exact failure mechanism, when exactly did it fail. Even the best of data has some a measurement error included with it. Yeah, Kevin, exactly right. That's what I was looking for, is the interaction piece. A simple block diagram assumes that each block operates independently. So if the power supply starts to overheat, it doesn't change the failure rate for the other components. Now, in practice, we know that of a faulty voltage through a circuit will affect many other parts of the electronics, or increase in temperature, or if we have a dampening system and it starts to fail, the dampening system may not actually fail completely, but it may damage some other part of our system. Take a shaft out of alignment and tear up the bearings. When we lose a little bit of margin on the ability of the system to dampen the vibration that it's receiving. And so it's a good idea to think through those and understand which ones are going to be, and I think you're getting at this, John, is which one is going to be, is you need to be aware of and create a huge impact on the final results you get. And understanding that the block diagram in and of itself is just a model. It just allows us to engage in a conversation as a way to help us inform our decisions that we're making. And so a couple of things to keep in mind. So let's go into a little bit of the basics, and then I've got a quick example also. But the fundamental, the easiest one by far is the series system reliability block diagram. I call it the weakest link model. And we just multiply the reliability of the individual blocks. And the simplest way to think of it is that, let's say I have a system that has 5 elements in it. We use an AND gate here to signify that all 5 have to operate in order for the system to be functional or to not have failed. And so we need all of them to go. With the way we typically do this is like a set of links in a chain. If any one fails, the system fails. And this is about as basic as it gets. We take the reliability over, say, the easiest one I remember and use all the time is, let's say I have a computer, and let's see if I grab my pencil here. Oops, I don't want that, I want that. I haven't used my marker in a little while, so I'll have to get a little practice here. So let's say I have a 2-year, or let's go with 1 year since it's and I want 95% reliability over the 1 year. It's my target. I hope it's not the new laptop I want to buy. I hope it does a little better than that. And if I know that I have to, the product of the individual blocks makes up the system reliability, I can use Excel or just a simple calculator and quickly find out that if I make each one of these things 0.99 or better, that the product of 0.99 to time the 5 raised to the 5th, or 0.995 times, is I'm going to get something that's going to be a little bit above my reliability goal. And that's great. That's what I'm looking for. But as soon as one of these things drops low, let's say it goes to 0.95, I'm going to blame power supplies because they're my favorite source of failures in products. It seems to be pretty common. And everything else has to be perfect, which is physically impossible given the nature of our systems. They may all last a very, very long time, and we may get close or approach 0.95, given that one part is at our system goal, but we won't achieve it. Now, remember that each block has some real physical chance of failing, and so it's going to be less than 1. And so each individual piece has to be a higher reliability than our system goal. Otherwise, we're just not going to make our system goal. And we may have a system that has a dominant error, just one thing that really drives all the failures, and everything else is really, really, really good. Well, then we can make the decision to ignore everything else and focus all of our energy on just improving that one weak link. That's fine. And that's just a system, a series system model, and it allows us to make some really basic decisions, fundamental decisions. I shouldn't say basic decisions, but fundamental decisions in the design of our product, right? And I apologize for my coughing today. Just got a little tickle in my throat, seems like. So here's a simple graph that if I have a number of items in series, if I only have one item uh, over time, let's say here's my 1 year mark. Get my pen out of here again. Right, so I'm here at 1 year. My reliability is, well, it's not all that great. It's a little bit above 60%. But if I add a second item that also has the same reliability, a failure rate of 50% failure per year, no wonder it's so bad. It's the failure rate is 50%, excuse me, 0.5, so it's pretty bad. But two systems then drop me to about 40% reliable at 1 year. And 3 continues to drop, and 4 and 5. And then you see it has kind of a diminishing return or diminishing degradation of the reliability. In general, though, if you add a lot of components, you just have more things that can fail. And especially if it's a series system, it just makes the reliability worse. So in general, one of the great things about, I think one of the only good things about a parts count prediction is that if you use fewer parts, you immediately improve the reliability. Now, the actual result you get from a handbook like 217 or the others are pretty much fiction compared to what you'll actually see. Yet it is true that if you use fewer parts and make a more elegant design, it will generally have a higher reliability. So the math supports that. If you just eliminate opportunities to fail, there's less chance to fail. So it basically works in that realm. All right, so this is all hopefully review for you. You already know this. All right. If you get into parallel systems, and there's not that many systems that we actually run parallel systems on. Now, I think the space shuttle program had 5 navigation computers on the space shuttle in order for it to navigate its way about space and get back to Earth. And they used 5 because it gave them an adequate amount of redundancy such that it would be exceedingly rare that they would have a failure where all 5 systems failed, and such that they would have the navigation capability to maneuver their spacecraft. Yeah, 386 PC processors probably. But I think they also use different architectures. They use different kinds of systems and such. When you really get into the high availability thing, you also need to be aware of common mode failures. So if I have a redundancy in a system and there's a common maintenance program that damages all of my redundant elements, then they all could fail for the same reason. So they're not truly redundant. So different architectures, different technologies, different systems can help to mitigate those common mode type failures. But it's amazing. I remember my old 286 and 386 PCs, and I'm glad I don't use them anymore. But when you add a parallel structure, you generally add some complexity. One, you're adding another component or another subsystem. But the advantage is that we use an OR gate then. So if I have 5 items, say 5 capacitors in parallel, and I only need one of the 5 capacitors to actually operate the system, then I only need 1 out of 5. And the OR gate means that it's just any one of these still working, the system still works. And we commonly draw it in a block diagram in a parallel structure. We use the drawing to show that there's multiple paths through to the system. Now, the key feature here is that the math, yeah, and you're exactly right, Mark. You can do 3 out of 5, and it's called K out of N, I think is the way I wrote about it on the Ascendo site. But if we're going to, one of the key things which I think makes this really easy is that if I'm using reliability for my individual components, the math is I look at the unreliability, in which case I can take the product of those, and then it's 1 minus that. Don't forget to bring it back out of the 1 minus, out of the unreliability state. And so it makes the math really simple. Now you can do this in other ways where you're using reliability directly without going to unreliability or the CDF part of it. But it can get complicated pretty quick. So this little trick here allows you to take even items in parallel that don't have the same reliability and quickly create an estimate for the value that it's going to have in your system. And by comparison, as I add components to the system, instead of one part that's a year and 3/4 old, take it here, it's about 40% reliable. If I add a second component that's still just as bad, I improve the reliability dramatically, and so on. The more I add, the more reliable I get. And it's pretty logical, right? If any one of these 5 systems can run the navigation computer for the space shuttle, I only need one of the 5 to work. And the chance that all 5 would be lost is rare. I suspect if they lost all 5 of them, they probably had lost a lot of other systems also. And so for critical systems, this idea of adding the extra weight or the extra complexity, the extra material, is a trade-off that was worth it for the criticality of that, say, navigation computer. In your product, it's a discussion, right? If I can't make my reliability, let's say I have a power supply that's just not quite good enough, and the next step up in reliability is very expensive, I may be able to use 2 power supplies in parallel that each one of them could run the whole system in order to achieve the reliability goal. And so it's the basic decisions like that in the design and the architecture of your product that a block diagram just helps you to accomplish and have those discussions with your team. Now sometimes, and there's many other examples, I think Mark mentioned a K out of N, let's say 3 out of 5 system. There's also all kinds of different parallel systems that deal with switches not being perfect, standby redundancy, warm redundancy, load sharing type things. So if I lose one power supply, the other one takes on a much bigger load and increases its reliability, or it decreases its reliability, increases its failure rate because it's on a much heavier load. There are variations, especially on the parallel side, to deal with all kinds of different circumstances. But sometimes we have a relatively simple system and we're trying to, say, add an extra power supply, right? And we just need this part of the block to be a little bit better. And we have the space, and it's a cost-effective decision to just put that one element in parallel, and the rest of the system's in series. Well, I like this example because it actually is pretty simple to calculate. Is you first take care of the parallel piece. Basically, we're going to reduce everything to a series system by simplifying these parallel parts. So I take the R2 and R3, their individual reliability, work it out so I get a reliability of this group of the R2, R3 pieces together, and then put it back into my model. Now it's a simple series system with straight line a product of the individual reliabilities. And it allows us then to, are we achieving our system goal, our overall objective? All right? And I think I've got an example. But for those of you that are using block diagrams, do they create the discussions like this? You know, where are our options? Where's the weakest link? What else can we do? I think my favorite use of block diagrams is, are we there yet? Have we achieved the system objective? So how's it working for you? Are you getting the benefit of the block diagrams within your team, within your organization. I think there's a big truck going by. Not sure if you can hear that or not. I can barely hear myself, so let him go by here. So if the block diagram is, sits on a slide deck someplace and he gets flipped through and no discussion, I submit that it's not really all that helpful for you at that point. If it's used on a regular basis, and Mark, the previous example, Willen, yeah, the idea here is that the block diagram is a way for us to communicate the impact of decisions on subsystems and of different parts of our product or system that impact the system reliability. If I'm working on the power supply, it gives me a context of how the reliability work I'm doing on the power supply impacts the overall system reliability, right? And so the parallel formula, William or Bill, is the product of the unreliabilities, and then 1 minus that, so you bring it back to the reliability performance of it. And then series systems, just the product of the reliability, of the probability of success factors over. One thing to keep in mind is that always use the same time frames. If I use reliability at 1 year, I should use that for the reliability. The time function should all be the same. Now you can use Monte Carlo and use the distributions. I could use exponential and Weibull and log normal, all in these different functions here, and use a Monte Carlo one to create a system distribution. It gets a little bit more complicated. But if I'm interested in, say, in my warranty period, say 1 year, I just set the time to 1 year for all of these reliability calculations. Yeah, exactly right, Kevin. Sometimes it's just, just showing the diagram. And here's our goals at one point, right? If I just put the goals, and say I have a 0.99 goal, and once we improve the power supply, we need to collectively have a 0.99, and I'll just use the straight line goals, right? Everyone's 99% reliable at 1 year. If our actual performance is, because we put this in parallel, we get a 0.995, say, and so like they're happy, they're good. But if my current estimate for this component is 0.98, and the other two we are assuming, we just don't know, but we have no reason to not know or to not believe they're at least 99%. They're usually pretty good. We could assume they're 0.99 or better. We can do the math here and determine if we're close to our system goal or not. And if we've achieved our system goal, this 0.98 is good enough. We're done. If increasing this is less expensive than adding the redundancy here, that's a trade-off analysis, and it allows our team to go back and forth to determine, well, should we add the complexity of redundancy, or should we pay a little bit more for other components to achieve what we're after? And so it's this comparison between the goal of what we want at the individual elements of our block diagram and the overall system to what we're estimating those blocks are going to be, or actually measuring them to be. And so the idea is that allows us to make decisions. That allows us to do trade-offs. Do we fix R1 or do we fix the R2-3 combination? Or do we have a different architecture, or do we approach this in different ways? At some point, if you just can't make your system goal, then it's a different discussion. Well, what's the impact on our customers? How important is this to our customers? What's our warranty cost going to be? How many spares are we going to need? What's the contract statements of it? What's the requirements that we need to achieve? And so the block diagram is a way to just create that incentive to talk about it, which is all good from our point of view as reliability professionals. At least I think so. I'd rather have people talking about it before we have field failures and before customers complaining. And yeah, so it's a set of estimates for us, and it allows us to have those discussions that allow us to shape our reliability planning for testing, our evaluations of suppliers, and what information do we need to gather from the prototypes we make and evaluate. Right? So block diagrams are, I think, one of the more powerful tools in our arsenal for the mission of, or for the idea of engaging the rest of the team in a discussion about reliability engineering. And so my last bit here is a story, and some of you may have heard this before. I see so many familiar faces, and thanks for coming in. But years ago, I was working with an organization that made a workstation, and they were losing market share. Their customers were not happy with their product and their product's performance. And these were workstations used for CAD drafting and for design of systems and so on. And so they had competition, and their customers were saying, hey, I can't afford to have my design team idle while your computer doesn't work. And so I'm going to buy somebody else's. So they were losing market share and revenue because of that. And the cited reason from their customers was that the reliability was not adequate for what they expected, what they needed. I need a system that's going to work hard for a couple of years, and then I'm going to upgrade to the next generation. But if it doesn't survive that long, every hour that it's down costs, I lose the productivity of that engineer that's design work there. And so it's one of those things that they were up against the wall. They had competition. They knew they had a reliability problem, and they started off a new program to improve the reliability of a product. And they were using a lot of the same design management techniques, the design reviews, the stage gate reviews, the reliability, setting a goal. But they were basically saying, we need to make it more reliable without a lot of substance behind that, which is how they designed the previous products. They were basically saying, we're going to design harder, not necessarily smarter. And so there's this one of the, I think it was the electrical engineering manager. They didn't have a reliability engineer on their staff or team. Very few organizations within Hewlett-Packard at that time had identifiable reliability or quality people, for that matter. It was just a function that the various other engineering disciplines had to take care of. So the electrical engineering manager had heard about a block diagram, and he just drew it. He says, it's a workstation. We've got a CPU, we've got memory, we've got power supply, and a few other of the major subsystems to our workstation. And so he just made a very, very basic series system model and filled it in with the straight line apportionment from the goal for how good they thought they needed to be, and then used just his engineering judgment. Is he guessed essentially and filled in blanks across the where here's where I think we are today. And, so the keyboard and mouse was doing great, where the power supply was doing pretty bad, for example. And he brought it to a staff meeting, their weekly staff meeting of their cross-discipline team with their program manager, and just laid it out and said, I just want to spend 5 minutes with it. Here's where I think we are today versus our goal. And this is a block diagram. These are just guesses. That's where we're at, right? And so it very, very quickly highlighted, and I'm picking on power supply. I don't remember exactly which one was their initial problem, but the power supply was going to drag their system down. The power supply consumed all of their budget for failures and more. And so the program manager, she was a brilliant woman, in my opinion. She turned straight to the power supply manager, the team that was sourcing the power supply and integrated it into the system, and said, "You're the weakest link. What options are available for us to improve the reliability of that power supply? Come back to next week's staff meeting with at least 3 options of how you're going to meet this reliability goal." And so at first it was they wanted to improve their estimate. So they went back to the vendor and found that they're still not there. Then they looked at what's the cost of getting a more robust, a more reliable power supply, and then what was the cost of doing redundancy, doing a redundant system on the power supply. And they came back to the team. They looked at their couple of options, and she says, "All right, great. Let's spend the money and get a more reliable system." And Phil quickly updated the block diagram and said, okay, CPU, the motherboard now is the weakest link. And so the program manager turned to that team and said, "You're the weakest link. Come back next week with some options of how you're going to achieve your reliability." And I think this program manager, she got the concept immediately that investing on the weakest link in a series system allows you to achieve your reliability goal effectively. You don't spend money and tell everybody to be more reliable. You don't give everybody individual goals and hope they can sort it out on their own. This allowed the team to support each other, to allocate resources, to shift talent from one to another, to shift funding or money to one to another, to focus testing on the areas that needed improved estimates and so on. So every week they started their meeting with an update to the block diagram, and then pointed at the next team and said, "What are you going to do to make improvements?" And then when it got close, there were 2 areas that were neck and neck to be the weakest link. She'd say, "All right, you guys work together and figure out what's the right option here to make the next increment of improvement." And as they got close to achieving their system goal, then the discussion said, well, as we are learning more about our system, is anything falling below our estimates? Is anything worse than we expected? And then what do we do about it? But it became just a few minutes in each staff meeting that allowed them to focus their team in getting the reliability improvements they were looking for. Now, the end of the story is that they ended up launching their product at half the failure rate that they expected that their target was. So it's much better reliability than their goal was. And the customers noticed immediately. So they were able to win back a lot of their market share and continue to expand their company and their product line. But it was just one person just put out a block diagram with estimates and got the conversation started. That's really all it took. All right. So hopefully you've enjoyed success with block diagram. And I noticed 1 or 2 people mentioned that they hadn't used it or don't use it in their current role or current job. As a reliability professional, and I'm making the assumption that many of you are, or if you're in the design or in the manufacturing world, you can use a block diagram from any position within the organization to just collect and organize the reliability data about your system. And it allows us to start, and I've said this, I don't know, probably 8 times already, is start that conversation about what are we going to do to improve the reliability. So weakest link is the easiest one to go after. More complex systems may require a more complex model, yet it allows us to take a look at the architecture and the fundamental performance of those individual systems in order for us to achieve our objectives, our business objectives. And by getting, if you find a champion that can drive that discussion, if you have a program manager or an ops manager that gets it and understands it and sees how it can be used, we could work to improve the estimates, gather the data, put it all out. But the people that are actually making the decisions, the electrical engineers, mechanical engineers, design engineers, manufacturing engineers, they're the ones making the decisions of what components we use, what material we use, and so on. So to a large extent, they need to be vested with updating the block diagram, of providing the best available information to make that a useful model for us to work. And so that's just one example I've seen that I thought was extremely effective at making it all work. So I wanted to share that one with you. So hopefully that makes sense. So I think the bottom line is that even a series system, very simple block diagram, you don't even have to draw it out in little blocks, although it seems to help on PowerPoint, but just a simple spreadsheet that lists your major subsystems and does the math quickly for you is really all you need to get it going. Let's see, a number of folks are typing here. Oh, okay, yeah, good question, Bill, on QFD. Um, yeah, and I should, let me pull up the where's it at? Conclusion slide here. It has where you can get the slides and the links for the other stuff here. So let me, and I've got a few minutes here, and I'll stay on the line and answer as many questions that come up. But yeah, Bill, you know, I'm not a big fan of QFD. I think the overall fully blown house of quality, multiple layers is a great concept. I've just never have seen it implemented very well. And it usually has such a burden of information that needs to go into it that it's not been all that terribly useful in practice. Now, I think the concept is great, and getting the early parts of the house of quality, basically we're talking about getting the voice of the customer. What does the customer want? And how do the functionality pieces of our design meet those requirements? Well, if you include reliability, if a customer is expecting reliability and it goes into that voice of the customer piece, well, then it affects pretty much all these other pieces that we're building into the system. So I don't know how to actually show how important reliability is versus all these other functional pieces other than a reliability specification. I think a block diagram coming out of that just makes a whole lot more sense than the house of quality if we're focused on the reliability part of it. The functions that are in our system may have lots of trade-offs, yet each function has the ones that are more important um, probably have a more importance from a reliability point of view also. And so I'm not exactly sure how house of quality helps other than it helps us remember to listen to our customers. And I think that's great. Now, for those that are interested in the the ASQ Certified Reliability Engineering exam, they just published a new body of knowledge. I just noticed it a couple days ago. I think they posted it at the start of the month, which gives them about 6 months of notice for those that are planning on taking the exam next year. The new body of knowledge goes into effect for the exams starting in January. And they dropped the QFD, the voice of the customer piece of it. I'm not exactly sure of the logic of that, but the topic of reliability engineers should understand how important reliability is to customers is not in the body of knowledge now. It's probably buried under the goals or business pieces someplace else, but which is fine with me because the only real tool we had before was QFD, and that wasn't widely used. So I think understanding our customer requirements is still important. Block diagrams, reliability apportionment is a great way of doing that. Right? Yeah, and you're exactly right, Jeff. The Monte Carlo techniques often start with just getting a good block diagram put together. And so you have that function of which to bring in all of those different factors, whether it's environmental or physics of failure models, that then dictate the reliability of those various subsystems. And of course, this can get real complicated, but even a simple one, and using Monte Carlo techniques, allows you to get a system level um, time to failure distribution based on the individual distributions of everything interior to it. And BlockSim is a good tool for doing that. I've used that a number of times. Those are good. Good questions. It's also questions I'm thinking I might have to use for future webinars. Those are good topics. Let's see. So, Robert, you're up in the questions tab here. Yeah, how detailed does a diagram need to be? Yeah, and I asked that question earlier. And I like the answer. I forget who said it, but said, it's to the vendor supplied systems or subassemblies. I also look at it as what are the critical components? What are the pieces that are going to cause failures for us? And so, is it if the valve is something that you need to consider in the trade-off and the balance of your system, then included the valve in the block diagram. But if the valve comes with a circuit board for a sensor system or controller that's not critical to the function of your system, I wouldn't break it down to that circuit board. So the hard part with models is you want to make them detailed enough so you make good decisions, but not so detailed that it makes it too confusing and too burdensome to maintain. So the model should support what you need to do with it rather than create the model and hope it's useful, if that makes sense. Freeware for simple RBDs, I just use paper and pencil. The formula, or Excel, or Google, their version of a spreadsheet, it's free. I think for the more complicated ones, there used to be a program called Raptor. I know that I think the software itself is free, but I think they sell training and support for it. And I have no idea. I haven't looked at it in a number of years, so I'm not sure what their circumstances. Yeah, so Kevin, is Raptor free and is it relatively straightforward to use? Because I know you can do really complex stuff with it, but at some point you need support. And yes, it's free. So that's a tool that you could use for even more complex block diagrams. BlockSim's pretty expensive from Reliasoft. I think it's a couple $1,000s to get started. But you can get it for free for a month. Oh, thanks, Jim. Yeah, I sent out a review of I started writing a review of the new the body of knowledge, and on Monday I sent out my first pass at it, which was just on what they removed. And so they removed, about a dozen or so different topics. And they have also added things and emphasized risk in risk management much more than the previous body of knowledge. So I'm going to, over the next couple of weeks, I'll be reviewing it in different ways. Otherwise, it's going to be a 5,000 word article, get way too long. But altogether, it'll be pretty interesting. 4,000 euros. Yeah, Mark, that adds up pretty quick. So yeah, take a look at Raptor. I used it years and years ago, and it was actually pretty straightforward to use and pretty easy to use. But if you're doing a simple block diagram, a spreadsheet works just fine. And you don't even need a spreadsheet. The math is actually pretty simple. So I avoid. Now, if you're going to do distributions and Monte Carlo stuff, spreadsheet's a minimum, but Raptor or BlockSim would be very handy. All right. Well, I'm going to stay on the line. So Kevin, this is Behringer1.com with a number 1 behind his name, if I remember right, and they offer Raptor on their site or some other tool. And let's see, checking the questions tab. Let me go ahead and end the recording. And thanks so much for participating and attending today. We'll